This is the third talk on Greenberg's model. Today I want to finish the discussion of how he thought about the classifying space of piecewise linear groupoids. Greenberg is probably mainly known for the work of Gies and Sergiesco, in which they use Greenberg's work to study cohomology of Thomson group, and also Takashi used his work on codimension 1 PL foliations. But his papers are interesting. Somehow I wanted to try to get people interested in type of the problems that he was trying to do, but apparently he passed away too young in an accident in the 90s. So recall what we did in the past two lectures. One thing that I want to say for those who were not here was that there is a Mather-Thurston theory that relate the group, the homology of the group, of the ambient group that you're interested in. So here, maybe the piecewise linear homeomorphisms of, say, compactly supported homomorphism of Rn to the homology of the classifying space of somehow the local versions of this, the groupoid version of this that is going to be denoted by gamma and PL. At the time of the Greenberg, this relation was only known in dimension 1, when n was 1. Okay? But now we know that this relation holds in any dimension. And I try to motivate that this space is interesting to study. And in the case of smooth, it's very hard to understand. In the case of PL, Greenberg has this inductive model that we're going to discuss today. One thing that I want to recall from last time, remember we talked about dimension 1, one particular theorem that I mentioned that for example, the consequence of taking Greenberg's seriously in all dimensions is that it tells you that the homology of the group homology of compactly or the PL homomorphism of a disk real boundary is 0 when this is 1 and 2, so it's perfect. The second homology is also perfect, so there is no interesting central extension if you're interested in central extensions. And I also mentioned, so this is not yet posted, but I also mentioned that the H3 is also trivial, at least rationally. So then that means that there is no analog of PL Gobelin way in codimension 2. However, this group is not acyclic, so it's not like that it's going to vanish in all degrees. That's a consequence of somehow taking Greenberg seriously. So I want to mention this and then to go to the classifying space of groupoids. And remember, here, the groupoid is given by groupoid of germs, but there is a topology on them. So it's not a discrete groupoid. That's going to be very important. So, one thing that I want to mention just to emphasize this point, actually one result that Greenberg was inspired by was due to Takashi, the following interesting fact, that in dimension 1, if you consider smooth germs of say def of R fixing a point at a point. So this is smooth diffeomorphisms. So let this group be G. OK, so from the category perspective, this is the automorphisms of a point in the gamma 1. OK, so the automorphism maps to the groupoid. So you can consider BG. Now, this is a discrete group. So to emphasize it, I'm going to use delta just to mention that this is a discrete group mapping to B gamma 1. And this is a smooth version of this. OK? So this is just the mapping 0 to 0 and mapping automorphisms of 0 to automorphisms of that object. So the theorem of Takashi says that this is trivial, this is null homotopic. Of course, this is KG1 space, and I said that this is at least 2 connected. So it's trivial on all homotopy groups, but that doesn't mean that it's null homotopic if something is trivial on all homotopy groups. This has, well, from foliation perspective, it's very interesting, but it also has some, amusing consequences. So for example, if you consider, smooth diffeomorphisms of R fixing the origin and map it to, say everything is orientation preserving for me. The entire diffeomorphism group of R, this map is trivial in homology groups. In group homology. OK?
Can you write bigger? I can't read it.
Sure. Is trivial in homology. And then from here, I'm going to write big. This map is just inclusion. It's a subgroup. OK? And this is an interesting phenomenon because you see this group, for example, even on the level of H1, this is not a perfect group because you can take a derivative at the origin. And the fact that this is perfect, it's not a trivial statement. But suppose that you don't know that this is perfect, then you can actually use this to prove that this is perfect. Because everything here is going to be in a commutator here, and then you can actually translate back to the origin and then write translation as a commutator and so on. And this is only H1. This is true in all homology degrees. OK? So this is already telling you that this category gamma is complicated. When you map the automorphisms into it, it's null homotopic in dimension 1. So if this were a discrete category, then this is supposed to be homotopy equivalence, because the groupoid is basically isomorphic to the automorphisms of just one object. OK? And the way one thinks about this is to think about how does germ actually act on something. So this is a vague question that I'm going to answer a bit later. So how does G, the group of germs, act on something interesting?
So you're going to write bigger.
Oh, thank you. Act on something interesting. OK. Question?
It's like a math trick applied to your writing. It just gets smaller and smaller.
Okay, so let me remind you the Greenberg's model in codimension 1. So Greenberg's model for B gamma 1 PL. So the way we talked about it last time, remember, so we had some subgroupoid of certain groupoid. We called them geometries, and the geometry was a tall groupoid over some topological space, which was a manifold X. And this was simple extension. And remember, simple extension had two properties. One of them was for some B in X. So let me remind what these are. So gamma is a groupoid. The morphisms is denoted by gamma 1, and source and target map to X. And gamma A is also a groupoid over the same objects. Okay? And this could be n-dimensional manifold. Okay? There exists a particular point B such that gamma orbit of B is the same as gamma A orbit of B. And so if U in X is open and G is a section of the source S, then there exists S locally finite set such that locally finite in so S in U intersections with orbits of B, such that when you restrict G to U minus S, this is in gamma A. So you're supposed to think about this as regular local homeomorphisms, and this is supposed to be the ones that are allowed to have singularities, but isolated singularities. Okay, and so again, these are topological groupoids. You can look at the germs at point B and the orbit of B and get a discrete groupoid. So definition, so let G, which is denoted by G1 to G0, be the discrete groupoid defined as follows. So here you see G0 is just given by the orbits of B. Say gamma orbit of B. And G1 is just given by gamma 1 maps between points in the orbit of B. Okay. Similarly, you can define the GA version, which is just the subgroupoid given by gamma A maps when you restrict to the orbit B. And then the theorem of Greenberg in this setting was, so I mentioned this suggestively as there is some diagram that you take the homotopy co-limit of. And this diagram I wrote suggestively as, G acting on Rn. You have to take the realization, really. So I'm going to something like this. There is a G also acts on Rn minus a point. I have to tell you what this means. You see, G is a group of germs that is really acting on B, but you want it to act on a neighborhood of B, which is somehow diffeomorphic to Rn. That's what you want, but you can make sense of it up to homotopy. And
Sorry, this maybe a stupid question. How do I know what n is?
what n is?
Yeah.
N is a dimension of x.
Okay.
X is a manifold.
Okay.
So the homotopy co-limit of this diagram is B gamma. That's the statement. Okay? So this basically tells you that if you're interested in B gamma, that is a groupoid of things that have isolated singularity, it's built out of the things that are smooth, with looking at how the smooth germs and the singular germ act in a neighborhood. Okay? This is up to homotopy BG. It's basically Rn bundle or micro Rn bundle over BG, if you know what that is. This is a sphere bundle over BG, and similarly for this. Okay? So let me quickly say how you could make sense of this action up to homotopy. So there is a technical lemma that when you have a groupoid G or gamma, so we say I denote by GK. So let GK be the NK of G. This is the K simplices. K simplices of G. Meaning that those are given by composable morphisms, K plus 1 composable morphisms. Okay. So here is a technical lemma. So let me remind myself what this says. So for every K and every G, say in GK, there exists an open set associated to G inside gamma K, which is the K simplices of gamma, such that the following holds. So first of all, G is in the neighborhood. Second condition is that the only singular thing in the neighborhood UG is G. And so face maps, so DI from UG to U dIg is homeomorphism onto its image and the degeneracies is a homeomorphism. Okay? So you want to think about it simplicially, okay? So you say that for every element in GK, which is given by composable germs, you can associate open set containing G, such that if G is singular, the only singular object in that open set is G, and this nice property for face maps and degeneracies. And then the way you think about that Rn bundle and Rn minus 1 is think about it simplicially. So definition, so you define the following simplicial spaces. So you define CK to be the disjoint union of, say, G in the K simplices of the discrete groupoid G, union of UG. So let me write in a different color. This is the realization of this simplicial space. When you take these local open sets and you build them simplicially so that the face maps and degeneracies make sense, and you realize this is going to give you the microbundle over BG. And then here, the sphere bundle is defined as follows. So this is, in Greenberg's notation, dk. dk is defined to be, again, disjoint union over germs of UG minus G. And this is the realization of this simplicial space. Similarly for GA acting on Rn minus 1 and GA acting on Rn. Okay? So in this way, somehow homotopically, you get to make sense of acting G on some small neighborhood around the orbits, and obviously there is a map from all of these spaces to B gamma. So you get a map from the homotopy co-limit to B gamma, and then to say that it's actually homotopy equivalence, you have to say something. That's the main point, actually, right? I'm going to just tell you some of the ideas that go into this. So he uses Siegel's techniques, so proof idea. Siegel has a paper on classifying space of foliations, something that he calls certain maps having almost local trivial maps. And the idea is, this is a realization of simplicial spaces. You first look at the levels. You look at CK mapping to, DK, and then say DKA, CKA, gamma KA. And so this is on the level of K simplices mapping to the K simplices of gamma, okay? And these are spaces. This is a space, and these are spaces. This is a disjoint union of open sets and so on. that you take the homotopy co-limit. It's a fact. If you think about what is called fast realization, when you have homotopy equivalence on the levels, you get homotopy equivalence on the realization. Okay? Suppose you want to use this, so then the proof boils down to show that you get homotopy equivalence on the levels. And these are, remember, these are non-Hausdorff manifolds. You have a map from a non-Hausdorff manifold to a non-Hausdorff manifold, and then you want to say it's a homotopy equivalence. Okay? And the idea is you show that this map has certain nice homotopical property that is called almost local trivial. It's not exactly fibration, but it's close. So that you can use the idea that, if I call this map Fk, if I look at the fiber of each point and show that it's contractible, then I get homotopy equivalence. This is not generally true. If you have a map between two spaces that the fibers are contractible, that doesn't imply that you get homotopy equivalence unless you have nice map.
Is Fk only defined on Ck? Or is it, you have like a diagram of maps?
You have a diagram of maps.
Okay.
Yes.
And the claim is that all of them separately are almost locally trivial, or when you take the homotopy co-limit of that picture, you get something?
All of them are almost local trivial, yes. I didn't define what it means, but it's very similar to microfibration, if you haven't seen.
Is this Carl Ludwig Siegel? Carl Ludwig Siegel?
It's Graham Siegel.
Okay.
Yes. Okay, and so this is already for codimension 1. For example, this implies, the formula that we mentioned last time. So when we think about, when we think about piecewise linear action on a line, so what is the thing that you have? Remember, so let's say gamma A, gamma acting on R. Then you can simplify this diagram. So part of the job that Greenberg does in 2 papers is that he has this main theorem that is a large diagram that tells you how to build B gamma. And then computationally, it's hard to think about it, so you have to simplify that diagram. And half of the paper is also about the simplifying the diagram. So in the case of acting on a line, the diagram becomes simplified as follows. So you have the right derivative and left derivative of germs from G to GA. So then you get the following diagram. So you get BG to BGA from right derivative, and then BGA from left derivative. You take the homotopy co-limit, you call this space R, and then you have a map from the smooth germs to R, and from smooth germs to smooth groupoids, and then the co-limit of this is B gamma. That's Greenberg in dimension 1. Okay? And if you think about it, both in the case of Thomson group and in the case of piecewise linear homomorphism group, this is going to recover this BR joint BR or S3. Just to say quickly for those who remember. So if you think about Thomson group, the germ is Z times Z, and then R becomes S1 joint S1. And then here you have BZ. B gamma A is also BZ, so it's BZ, BZ, S3. The homotopy co-limit is going to be S3 again. That's how S3 shows up in Thomson group calculation. And for piecewise linear of R, it turns out that this map is always homotopy equivalence. It's a It's a nice fact, actually. For those who come from Caesar congruence, this goes under the name of central Kiel's lemma, something like that. And then you get homotopy equivalence between R and B gamma in that case. Okay, so that's the codimension one. I want to tell you about higher codimensions. Part of why Greenberg is known, I mean, he was really algebraic topologist. Why he's known to group theorists perhaps was there are many interesting subgroups of piecewise linear homomorphisms. You can define the following general groupoid that Greenberg considered. So now higher n. So let K be a subfield of real numbers. Okay? And then you can define the groupoid gamma GK as follows. So these are given by, so this is given by, local homeomorphisms of Rn that when non-singular, so when regular, it's given by some affine map whose linear part is G and translational part is given by K to the n. Okay? When regular is given by let me write it this way. And the singular parts and singularities are in a union of hyperplanes with coefficients in K. Okay? So you not only can consider piecewise linear homomorphism of, say, R2, R3, and so on, you can restrict to subfields and get many interesting subgroups. When G is GLN and K is the entire R, we know math at Thurston. So we know that B gamma is related to piecewise linear homomorphism of Rn. If you change G as a subgroup of GLN and change the field, we don't know how it's related to the ambient subgroup of these things. And you can play with this. This is something that actually Greenberg does. So you can, one interesting example that he considers is when G is SLN Z and K is Q, or I should say SL2Z, he actually calculates what the homotopy type of B gamma SL2ZQ is. It's homotopy equivalent to rational S2 veg with something that he calls RS3, and RS3 is given by the following diagram. Loop on S3 to S3, homotopy quotient by the S1 action is going to give you RS3. It doesn't matter what this is, but the point is you can explicitly understand the homotopy type. And what is interesting is that you can extract invariance for piecewise SL2Z homeomorphisms from this homotopy type. This rational sphere tells you about the area, for example. It has to preserve the area, of course. Okay. Any question before I tell you how to understand the homotopy type in higher dimensions? All right. Okay, so in dimension 1, well, the singularities are isolated. But already in dimension 2, singularities are going to be complicated and stratified. And we have to try to understand, the one way of indexing the stratification on the singularities already on the plane. Okay, so if you think about, say, piecewise linear homomorphisms of R2, or some subgroup of it. The singularities, it could be given by some linear object. It could have maybe given by two things that match on some line. It could be given by a bunch of chambers that are given by some matrices on each of them that they match on these lines and so on. So we want to, you see, it's naturally stratified. Okay, so we want to index how we are going to think about the singularity set, and then so that we can glue these things together. Okay, so let me define some notions. So definition. So for G in, say, gamma GK, at a source, so the singular set of G is subset of some union of hyperplanes. Okay, so these are hyperplanes. Okay, and Greenberg calls NING, this is a strange name, it's actually intersection singular set. I don't know how he abbreviated to NING, but or the intersection singular set of G is defined to be the intersection of these hyperplanes. Okay? And then the dimension of the germ is defined to be the dimension of NING of G. So the way that you're supposed to think about it is if the dimension of G, if the dimension of a germ is 2, it's actually non-singular. So this is, so G is affine. If the, say n is 2. If the dimension of G is 1, G has a crease singularity. And if the dimension of G is 0, then you have at least, say in R2, you have at least 2 lines of singularities. So there is a fixed point and at least 2 lines. Okay, so it's given by, so the singularity is the boundary of chambers. Okay? So we want to index these singularities by flags. So let me define what I mean by flag. So definition. So here, let I be set of increasing sequences, say I1 integers, I2 dot 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 ik, and by affine I flag, we mean a chain of subspaces f1 dot 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 fk, such that the dimension of fi fj is ij. And FIs are, affine subspaces of Rn. Fi is K affine. Yeah. And one notion is that if I denote I flag by just F, which is the chain of F1 Fk, Greenberg writes the absolute value of F to be the last one over R. Okay, that's just definition. He calls it the support of the I flag is given by the last one when you consider the extension of your field. Oh, I shouldn't erase this theorem just to compare it with the higher dimensional version. So in a higher dimensional version now, you want to here, because the singularity is isolated and you just have a bunch of points, you have some distinguished orbit, you look at the germ of the gamma maps at that point. Now, the singularity can be, a bunch of hyperplanes. So you're going to have many of these things that you have to take the homotopy co-limit of. But let me tell you how you actually organize them.
Are these hyperplanes affine, or they pass to the origin?
Affine, yes. Right. One thing that you can do is, maybe another definition before I say this. When you have a germ, let's say G is in gamma GK, of course you're thinking about G going from some point to some point. And it's a germ of a piecewise linear homeomorphism. Okay? So locally, maybe the singularities are given like that. But then you can, if you just look at the germ of a PL homeomorphism, you can actually extend it canonically to the plane. So note G has a canonical extension to a map from, say, Rn to Rn, such that the germs are the same. So G at P is just G. Okay? So when you have a piecewise linear homomorphism, you have this. Okay? And the idea of Greenberg is that, you see, I mentioned at the beginning that when you want to understand the classifying space of a topological groupoid, it's going to be far from the automorphisms of each object, the germs. The germs might be null homotopic when you map them to the entire thing. But he wants to think about B gamma as using generators and relations, saying that, oh, I know that I can understand germs by just looking at PL homeomorphisms, say mapping a pair P to Q or even just P to P. And then I have to introduce relations, because when I consider germs and then when I extend it to Rn, different germs might have the same germ at some other point. So I have to somehow mod out by that. And the way he does it, so let me maybe explain one part of a diagram. Remark, let P0 be the group of gamma GK homeomorphisms fixing 0. Now, similar to what I said before, you can make sense of the following. So P0 acting on Rn minus 0, mapping to P0 acting on Rn, and mapping to some groupoid gamma 0. So let me.
Could it be here that I can make sense of that? So that uses lab technical lemma with C's and D's to write down things like that.
Here it's easy because
it's fixing the origin.
Fixing the origin, yes. So what do I mean by gamma 0? I should tell you what gamma 0 is. Okay, and the gamma 0 is supposed to be the quotient of the action of P0 or R n minus 0. So, so gamma 0 is a groupoid. The objects are given by Rn minus 0. And the morphisms are given by quotient of that action category P0 on Rn minus 0, where you say two things are the same if they have the same germ, so quotient by germs. Okay, and this is where he calls this Reb component of the diagram. And this is where actually projective homomorphisms naturally shows up, because P0, what is P0? P0 is a piecewise linear homomorphism fixing the origin. And if you have a piecewise linear homomorphism fixing the origin, you are projectively acting on the link of 0. And that's actually the isomorphic group. If you consider, say, piecewise projective homomorphism of the sphere, that's just the same group that you want to understand. And gamma 0 is given by, now, remember Greenberg, when he talks about groupoids, he thinks about geometry. So it seems that you are thinking about sphere, which is the link of 0. And you are thinking about, local maps on sphere that is going open send open sets on sphere to another open set by piecewise projective maps. And that's the groupoid gamma 0. So you see, this is using the language of flags. This is somehow the deepest part of the stratification, that you have one point with many hyperplanes passing through it. And you can imagine that you have rep components for each I flag. You fix your flag, you fix your piecewise homeomorphisms, fixing that flag, and then it acts on the complement of the flag, and so on. So I'm not going to define it for the interest of time, but this is the deepest part of the stratification, and for each flag you get the same homotopy co-limit. So I'm just going to say as a remark, so for each I flag, there is a map like that. There is a pi mapping on. I have to think about the right dimension, but I'm going to say S n minus dimension of the I, and then bpi b gamma I. And then you can see that this is a subscript. And if index I is included in index J, then you have a restriction on the level of stabilizer. So you get a big diagram that you have to take the homotopy co-limit of, and that's going to recover B gamma. But then how is it useful? The final interesting part of his theorem is that if you consider the entire piecewise linear homomorphism of Rn, that one rep component is enough. So instead of just writing some vague statement that the homotopy co-limit of this big diagram is going to tell you what this B gamma is, in a case of when G is GL and R and K is R, that is enough to say what B gamma GK is. So P0 fixing, acting on Sn minus 1, BP0, B gamma 0, tell you what B gamma NPL is. This is theorem. Okay, and this is actually, this advocates trying to understand projective homeomorphisms of sphere of any dimension. This is the piecewise projective homomorphism of the sphere. This is the sphere bundle over that. This is the groupoid version of piecewise projective on sphere. And then it tells you what B gamma NPL is. And this has inductive flavor because these are geometries on sphere of one dimension lower. Piecewise projective is really acting on Sn minus 1. So you can inducting back to lower dimensions. So I use this in the case of n equals 2 for those theorems. In the remaining time, I want to tell you one interesting calculation that he does. But any question before I end with this example?
So the B0 is just a group, like a discrete group.
Yes.
How do you understand the B gamma 0 part?
That's the inductive part.
Okay.
Yes. You can do exactly the same thing to understand B gamma 0. Again, using flags of singularities and so on.
Why does he invoke Grape's name? It's a connection with grape foliation.
Yes, I mean there's a good reason. In dimension 1, somehow the fact that in case of Reb, you have one compact component, and then you look at the two sides of that component. It's going to, if you let n be 1, that's going to give you exactly that. You're going to have two components around the germ, and that's going to actually recover the torus. But OK, actually, this example is interesting. So I try to be quick but understandable. This is actually related to Caesar congruence. So he considers the following interesting object. Suppose in R2, you consider the following object. If when you have a map from interval to R2, I say it's a K PL map if F has finitely many singularities, and when F is PL, and when F prime is not defined, Fx lives in the coordinates of F are given by your field K. OK? Now, define the following one manifold. So let Mk, this is your subfield. You can let it be Q or R or something. This is defined by the disjoint union of these intervals with maps taking quotient by PL germs. So this is quotient by PL germs. So what do I mean by this? So if you have two maps, say A, B to R2, these are embeddings. I should say embeddings, PL embeddings. And G from, say, CD to R2, and a point here X and a point here Y, and a neighborhood here U, and a neighborhood here V. So I say the class of, pair Fx, the germ of Fx is the same as the germ of Gy. If there exists a PL map here that make this commutative, so H PL map. OK? This is I'm going to end in 2 minutes. This is an interesting object because it's a one-dimensional manifold, but it's a non-Hausdorff one-dimensional manifold. It has a large H1 on which piecewise linear homomorphism of the plane acts. Also, the pseudogroup acts. So then you can ask some sort of Caesar congruence group for this. So let me say, gamma GK acts on this. So you can make sense of this, and then you can consider H0 of this groupoid with coefficients in H1 of this manifold. OK? And Greenberg uses his model to calculate this. And the calculation is interesting. It's Z plus Q plus Q. For, G is SL2Z. and K is Q. And this Z geometrically is the winding number. One of the Q's is given by the area of your cycle. So you see, cycle here is like a lattice polygon in R2. And then this groupoid acts on this lattice polygon, and it tells you that you have three invariants. One is winding number, one is area, and one is some sort of length. Okay? And later he shows that if these invariants are the same, actually you have a global piecewise linear SL2Z map from one polygon to the other. Okay, thank you. Yes.
Sorry, what is the winding number for these polygons?
It's a curve in R2. Any one cycle in MK is like a closed curve in R2. And any closed curve in R2 has a winding number.
It's like a turning number? Like how
Yes.
many times it's turning around?
Yes,
Oh, okay.
yes.
Not like winding around a particular point in R2.
That's right, yes.
Okay.
Yeah, I mean, Greenberg has a paper called Smooth Caesar Congruence. The smooth version, he calls the smooth version of this acting by area preserving groupoid. And then it's going to be Z plus R in that case. You don't have a notion of length there. Yes.
It seems that for geometric reasons we maybe want to compute B gamma bar instead of B gamma. Is there a way of simplifying these diagrams for this computation? Is it just you have to compute B gamma and then you have to take the fiber?
For n equals 2, I did the latter. But I agree. It's kind of annoying that somehow B gamma bar is the interesting object and you want a description as a homotopy co-limit of that. I haven't figured out whether there's the same state. Yes. All right. Well, if there's no more question, we will resume at 1:30.